Okay, so what we're going to do here is we're going to start training the network that we just built. So to do this, we'll start off by importing the general torch library. This will give us some more functions that we could use to train the network. And then we'll define the size of our inputs. Remember, we needed that to start our network. So if you look at my data shape, this is 0 and this is 1, and this is the size of your inputs. So we're going to access the first index. Then we'll do the same thing with size outputs. And if you look up at the shape of Y categorical, again, first index, we have 14. The reason I just don't say 14 and 30 is so if we decided to engineer some other features, we don't have to keep changing that. Dot shape 1. Then we'll have to create an instance of our neural network. So we'll do that by saying my NN is the neural network that we just created, and we'll pass in the inputs and the size of the outputs. Then we need to define our criterion, and this is the metric that helps us measure our error and loss. So it's a classification task. We're going to use the binary cross entropy loss that we talked about in one of the last videos. Then we need to define our optimizer. We need to define how we step towards the global minimum. How do we reduce error? How do we move towards that? So we're going to use an optimizer called the Atom optimizer. It's an adaptive algorithm that adapts as your neural network trains. It performs very well. It works very efficiently. So for our purposes, it should suffice. Most people will customize their optimization scheme and they'll use things like step learning rate, but that really only improves you by a small percentage. In the industry, that small percentage could matter a lot, so that's why they do it. But for us, we're just learning. We want to get a neural network to work, so we'll just use the Atom optimizing algorithm for now. And then I also want to import something from a general machine learning library called sklearn. We're going to import the test trains, or the train test split. sklearn is a general machine learning library. The difference between PyTorch and sklearn is that PyTorch is a deep learning library, which is a subset of machine learning. So sklearn will have other types of algorithms such as support vector machines, but really we just want this thing called train test split. So what we want to do is we want to get our X training data, our X test data, our Y train data, and our Y test data. And what we're going to do is we're going to call the train test split. The reason we want to split our data set into testing and training sets is because we want the neural network to learn some patterns. We want it to learn how to tell what a dog is. So we'll show it some images of dogs. And then we want to show it a completely different picture that it's never seen, and it should be able to tell that it's a dog as well. So we need the training and testing data set just to make sure that our network is able to generalize to cases that it's never seen before, because if you just show it everything, you're at risk for just memorizing those details. So to do this, we'll pass in the input data, the output data, which is called Y categorical. And another tricky thing is, how do you define the size of these? We want our network to have a very large training data set. So we don't want to give too much to the test data set. But then at the same time, we also want the test data set to accurately demonstrate how well the model is performing. We want to have a test set that's sufficient enough to demonstrate that the network is able to generalize to a lot of different cases. In practice, 20% or 30% of your data could go to test set. That way you have 70 to 80% for training. So we're just going to set 20% to our test set. Now, what we need to do is a little bit more processing on the data so that we could pass it through the network. Now what we need to do is convert our data into a float tensor. A tensor is just the most general representation of data. Everything is some type of tensor. So a set of variables, like what we have, that's a rank 1 tensor. A matrix of numbers is a rank 2 tensor, and a stack of matrices, maybe like a RGB image, you have 3 layers, that's a rank 3 tensor. So any type of data could technically be called a tensor of a different rank. But in order to process the data, we need to make sure it's in the form of a tensor, and that's what we're doing here. So we're going to pass in, we're just going to convert everything here. Okay, and then just to test to make sure that all our data could run through our network, let's say results, we're going to pass our training data through our network, and we're going to try to calculate an error for those results. So what measures our error is the criterion, and we're going to compare our predictions to the expected values. So train y. And we're going to print some of the results. We'll print the first 5 results, and we're going to print the error. And let's run that. Looks like I forgot to run the neural network block. Okay, that was weird, but okay, we got our results. So we know that it's calculating some predictions, and then we're able to generate an error. 0.72, it's high, but we're just starting off. We haven't trained it yet, so that's okay. So now we'll get into the training. So let's start a new code block. First, we want to define the number of epochs we want to train for. In general, the longer you train your model, the better it should perform, but it doesn't always work that way. There's different things that could come up that prevent this from happening, like maybe it approaches a local minimum, and then maybe your data set isn't sufficient enough to converge to a lower point. But anyways, we're just going to set this to 500. Next, we want to track how our model trains. So we're going to store the losses into these variables. And what we want to see is we want to make sure our test loss performance is at the same level as our training loss performance. That helps verify whether or not the model is able to generalize to the other cases that it's never seen before. So now we could get into training. I'm going to create a function called train test. And the reason I'm going to combine the training and testing function together is because it's basically the same thing. For training, you backpropagate your error. In test, you don't backpropagate. You don't learn from it. So we're going to pass in the network we created, our inputs, our labels, our optimizer. We'll set it equal to none as a default, but we have it, so don't worry about this. And then we'll also have a mode, and we'll set the default mode to train. Now, in order to train, we need to generate some predictions. So we'll say network inputs, and then we need to generate an error. So then we'll say criterion, and we'll compare the predictions to the expectations. Now, this is where it's a little different. If your mode is train, then backpropagate your errors. But what we need to do here is we need to zero out the gradients. The reason we have to do this is because PyTorch stores the gradients as you're training, and at every iteration you don't want to stack them up. You don't want to accumulate the loss. You only want to adjust for the loss at that epoch. So you just need to zero out the gradients and reset them. And now what we're going to do is we're going to backpropagate our error.backward. It's as simple as that. Then we're going to take a step with the optimizer. We're going to take a step and update the weights here and hopefully go towards the global minimum. And after you're done with that, we're going to return our predictions maybe. We might be interested in seeing what the network predicted, so we'll have that there. And then we're going to return our losses. Now, the reason I say item here is because when it stores your gradients, it stores it as a graph, and we only want the number. We only want to see what the error is. So now we have our training and testing function. Now, in order to train, all we have to do is say for I in range num epochs. So for every epoch, that's all that's saying. We're going to do, I don't want to show the predictions right now. That's something that maybe we could do later. And I'm going to call the train and testing function we just created. We're going to pass in our network we just created. We're going to pass in our inputs. I forgot what we called it. We called it train X. Train X. We're going to pass in our labels. So I believe it's called train Y. Our optimizer, which we called optimizer. We're going to pass in our criterion, and then mode is train, because we're going to train here. We're training with our training set. So once you generate the loss, just append the loss to the training loss variable. Next, you might want to track the test losses. So we'll do the same thing here, except we don't need the optimizer and criterion anymore because we're training. I mean, we're just testing, so you don't need to backpropagate your errors. We just want to see how it generalizes to different cases, and then append your loss here. And then we might want to plot the losses and see how our model performs as it trains. And then we'll create a legend just so we know which one's which, and we'll do plot that show. And that's it. We could run this and hopefully we get some decent results. I'm sorry, we do need the criterion because we do want to see what the loss is. I'm a fool for this one, but we called it criterion though. Criterion equals criterion. We need to do this because what I did earlier, it was reading the optimizer as criterion. So again, I'm a fool for that, but I'll admit to those mistakes. Okay, so we have the graph and we'll see that training is actually improving. So we started with a 0.7 error, and then we go down all the way to around 0.1. But there's something I wanted to point out here. See this little separation that's occurring? That means that, so orange is the test loss and blue is the training loss. What's happening here is something called overfitting, where it's performing better on the training loss than on the test loss. We want these graphs to perform similarly, but in this case it looks like it's about to diverge and it's overfitting. That's okay, that's something that commonly happens, but it's something that's good to know. Usually you want these trends to go the same way. Now, one thing I should point out is this graph is really smooth, and this is not something you'll see when you start looking into more machine learning and deep learning types of projects. Usually they're very noisy, but I think, I'm not 100% sure, but I think the reason for this is because we trained on all the data at once. So what happens in other deep learning projects is we create batches, and that's something we'll do in the next set of videos when we start working with convolutional networks. But we put the network into batches, so it's only learning on a very small part of the data, and then it learns on another small part of the data. And that could cause those graphs to be really noisy. But here we train on everything, and I'm pretty sure That's why it's so smooth. But if I'm wrong, if there's something else that you might know that I don't, please let me know. That's just my best guess as to why that happened. But something I did want to do here is print the loss. So actually what I'm gonna do is call this chain loss. Okay, so there's a problem here. It's the same name, so I'm just gonna say training losses. Gonna make it plural this time. And then we're gonna do test loss. And just so we could see how it's training in real time, I'm just gonna say print at epoch I. So that's just the epoch that we're on. We're gonna say training, I should put a comma here, training loss is train loss, and then test loss is test loss. And now what I'm going to do here is reset the network, because it's already at a stage where it's learned a little bit, but I want to see it progress again. So let's run this again. So we could see that it starts off at around 0.7, and then you'll see that it's decreasing as it trains. And you could check this before you even produce the graph. So that's why I wanted to print it. And again, it's overfitting. There's some ways to avoid this, but it's something that we could accept for now. It doesn't look like the separation is too large anyways, so we can live with that.